Today we are taking a look at inverse functions and relations. A relation is any set of ordered pairs. Some relations are functions, but not all of them. Remember, a function is when each input, or x value, is paired with at most one y value. So when you're looking at a relation, if it fails the vertical line test on a graph, or if you're looking at a set of ordered pairs and you see the same x value paired with more than one y value, it is not a function. Inverse, of course, undoes an operation or a function. Some common examples of inverses: addition and subtraction, multiplication and division, square rooting and squaring. So the process for solving for the inverse of a function is to switch the x and the y and solve for y. We're going to see some basic inverse functions today, and then tomorrow we're going to see some of the more challenging ones. Horizontal line test is used to determine if the inverse of a relation is a function. So the initial relation might not be a function, but its inverse could be. Starting with our first example, we're given a relation, just a set of ordered pairs, and we're asked to determine whether or not it's a function. So when you're looking at the relation, again, look at the x values. The y values can repeat. Think about a parabola. You've got 2 squared is 4, and negative 2 squared is 4, but it's still a function. So the y values can repeat, not the x values. So when we look at our x values, we've got 1, 2, 3, 4. They are all unique, so yes, this is a function. The inverse is when you switch the x and the y. So the inverse relation, we haven't looked to see if that's a function, would be 2, 1, 4, 2, 6, 3, and 8, 4. So looking at whether or not the inverse is a function, now looking at the new x values, 2, 4, 6, 8, are all unique, so yes, the inverse is a function as well. So now what we're going to do is plot both of them on the graph, starting with the original relation, or the original function, 1, 2, 2, 4, 3, 6, and 4, 8. So there's our original relation. Now we don't know whether or not we should be connecting them with a line. It does look pretty linear, but the relation was just those 4 ordered pairs, so we're going to leave them unconnected. The inverse, graphing that, 2, 1, 4, 2, 6, 3, and 8, 4. Again, it looks linear, but just those 4 ordered pairs are our inverse. And the one thing that I want you to notice graphically is that the relation and the inverse are reflected across the line y equals x. So think about that diagonal line that goes through the graph. That's the y equals x. And remember, to get the inverse, we switched the x and the y. We flipped them across the line y equals x. To show that two functions are inverses, we do a composition. So we start with f of g of x, putting the g function entirely into the f function for x. So that becomes 7 times the quantity 1/7 x plus 2/7 minus 2 to finish off the f function. Distributing our 7, following order of operations, we would get 1x plus 2 minus 2. And of course the 2 minus 2 cancel, leaving us with x. Remember, functions that are inverses undo each other. If you substitute x into one function, put that answer into the other one, you get back what you started with. So think about a more simple operation, which is squaring and square rooting. So if we take 5, square it, we get 25. Square rooting it, we get 5 back. So we get back what we started with. So in this case, it looks so far like they are inverses because it worked for the f of g of x composition. But we have to check the other way too. G of f of x, taking our entire f function, the 7x minus 2, and substituting it into our g function for x, This time we get 1/7, 7x minus 2 plus 2/7. Distributing our 1/7, we get x minus 2/7 plus 2/7. And again, those cancel, leaving us with x. So those two functions both undid each other to give us x back, so they are inverses. Last example, we're going to find the inverse and then graph both of them again, remembering that they should be reflections across that line y equals x. So it's kind of a check on how we did finding our inverse. So we're going to start by replacing the f of x with y, switching the x and y, and solving for y. So I'm going to add 5 to both sides. And dividing everything by 4, we get 1/4 x plus 5/4 equals y. Or we can use our function inverse notation, f inverse of x. Graphing the original one, we're going to start at our y-intercept of -5. And we had a slope of 4, so we're going to rise 4, run 1. And for our inverse function, we have a y-intercept of 5/4, which is a little bit more than 1. My calibration's a bit off. And then our slope is 1/4, so we're going to rise 1, run 4. Or we can fall 1, run 4. Oh, that's way off. So something kind of like that. And again, picture that y equals x line. Maybe get that a little bit accurately. And notice how there are reflections across that line. And you try.